A very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be talking about velocity gradients. So let us get started. The topics for today's discussion will be as follows. We will define the velocity gradient tensor first, and then through that we will define the rate of deformation tensor, which is one of the most important tensors when talking about continuous deformations. After defining this rate of deformation tensor, we will discuss its interpretation, that is, both the diagonal terms and the off-diagonal terms. So let's get into a discussion on the velocity gradient tensor. So when we talk about fluids or say plastic flows, in those situations when there is a shear stress applied on the material, that is fluid or the plastic, flows continuously. So what that means is that the material keeps deforming continuously. So in these cases, it is not the displacement that we talk about, but rather we talk about the rate of displacement of the material, which basically is the velocity of the material. So we define the velocity field, which is the vector v, as a function of small x and t. So this is the Eulerian description. And the Eulerian description is important in this case because we're talking about a continuous deformation. So the material configuration does not matter. What matters is what is happening at the current state at a given spatial location. So analogous to displacements, here we have velocities. So just as we define the displacement gradient tensor in solids, we define the velocity gradient tensor. And we call this the spatial velocity gradient tensor. So it is called spatial because the derivatives are with respect to the spatial coordinates. So Lij is an important tensor in fluid mechanics, and we can split this velocity gradient tensor into a symmetric part and a skew symmetric part. So this is the additive decomposition, and this symmetric part is called the rate of deformation tensor. And the skew symmetric part is called the vorticity or the spin tensor. So Dij is the symmetric part, so it's defined as half of Vi comma j plus Vj comma I. And similarly, W is the skew symmetric part, so it's defined as half of Vi comma j minus Vj comma I. Now please note that we write d as a rate of deformation, but d is not equal to a d by dt of the deformation gradient tensor. So there is a confusion sometimes because of the naming, so we must be careful with that. Now when we talked about solids, we talked about this additive decomposition, which is valid for infinitesimal deformations. So what we said was that the symmetric part of the displacement gradient tensor was the infinitesimal strain tensor, and the skew symmetric part was the infinitesimal rotation tensor. But in fluids, there is no condition on these tensor components being small. This is a very important point, so we must write it down. So let us put this tensor Lij, that is the spatial velocity gradient tensor, to use now. So mostly we work with spatial coordinates in fluids. So there's no need for a material coordinate system because the fluids are continuously deforming. So we just take the current configuration and analyze what's happening to it. So in this spatial coordinate system, let's say this is a point small p around which we are interested to evaluate the deformations or the rate of deformations. And we take a point q. Now this point q can change, and this will help us analyze the rate of deformations of different points around the point small p. So all the quantities such as Lij, Dij or Wij will be defined at the point P because our analysis is around the point P. So this vector joining P and Q is our d small x vector. Let's say the velocity of the point P at that instant is v, and the velocity of point Q is some v plus dv. It is very similar to what we had discussed in solids. So the velocity of point Q, which is close to point P, is the velocity at point P plus some differential velocity. So it is this dV that we'll want to quantify, just like we wanted to quantify du in solids. So this dV, which is actually the relative velocity of the point Q with respect to the point P. So this can be given as partial, let's use the initial notation. So dvi becomes partial vi by partial small xj times dxj. Remember, the velocity v is expressed in terms of its spatial coordinates. So we can write dv in the symbolic notation as this was Lij that we had defined in the beginning of the lecture times the vector d small x. So the velocity gradient tensor helps us find this relative velocity of any point q around the point P using the velocity gradient tensor and the vector dx, which is the vector joining the points P and Q. So as I move my point q, my d small x will change, but this quantity Lij is fixed for the point P, so this will not change. So if I know the quantity Lij for a given point P, I can find the relative velocities of all points around the point P by simply moving the point Q, which results in different dx values, and the corresponding dv's are obtained. So now let us try to link this quantity L with the quantities that we had obtained in solids, because we're talking about rate of change here. So let us see if we can link this L to the quantity F that was the deformation gradient tensor in solids. So the velocity gradient tensor can be written as del Vi upon del capital XA times del capital XA upon del Xj. Now we are bringing the material coordinates here to be able to link these quantities to the quantities that we have defined for solids. However, there is no general relevance of the material coordinates in this situation. So we assume that the material time derivative, that is d by dt, and the material gradients, they commute. So this Vi can be written as d by dt of xi. So I take the d by dt outside. So this becomes del xi upon del capital XA times del capital XA upon del small xj. So our Lij, that's a spatial velocity gradient tensor, that is a d by dt. Now this quantity del small xi by del capital XA is nothing but our deformation gradient tensor f Ia, and this quantity del capital XA upon del small xj is the inverse of f. So that's the aj component of f inverse. So in the symbolic notation, L can be written as f dot. So I use a dot on the top to denote time derivative times f inverse. So now we can see that we've been able to write the velocity gradient tensor in terms of the time derivative of the deformation gradient tensor. I can also write f dot as L dotted with an F. So these relations we'll be using at different stages during analysis in this discussion on the kinematics of fluids. So now that we have defined L and its relationship to the deformation gradient tensor F, let us do an interpretation of the different terms in these tensors. Now again for discussion, I'll be using material coordinates, but as I said in fluids, material coordinates are not that important. So it's only for the discussion that we start using the coordinates, but eventually they'll be not of any use in the result. So let us say we had a material fiber or a material element d capital X, which was in the direction of capital N hat vector, and this got deformed to a d small x in the current configuration, and the vector corresponding to d small x in the spatial configuration is small n hat. So we had defined the stretch ratio lambda capital N hat as the ratio of d small x magnitude to d capital X magnitude. So with this, let's write the d small xi vector as Fia times d capital Xa. So with this dxi, I multiply by the magnitude dx and divide by the same quantity. And on the right hand side, I multiply by d capital X magnitude and divide by d capital X magnitude. So this gives me d small x times the vector ni equals Fia times d capital X times the vector capital N A. And if I take this d capital X on the left, what I get is the stretch ratio lambda capital N hat times Ni equals Fia Na, or in the symbolic notation, this becomes lambda times the vector small n equals F dotted with the vector N hat. I'll box this because we'll be using this in the subsequent discussion. So if I take the material derivative of this equation above, what I get is lambda dot times n hat plus lambda times n hat dot equals f dot times n hat plus f times n hat dot. So the dot on the top denotes d by dt of the quantity. Now this quantity capital N hat is defined in the material configuration, which is independent of time. So this quantity becomes a 0 because capital N hat does not change with time. Now this f dot was defined as L times f, so I can use that here. So this becomes L times f dotted with an n hat, and this f times n we just defined as the stretch ratio lambda times small n hat. So we can write this as L times lambda times n hat. There's a dot here, or more conveniently, I'll write lambda times L dot n hat. In fact, I can divide both sides by lambda. So this is what we get. So what we have is a lambda dot upon lambda times n hat plus n hat dot is L times n hat. So please remember that we are trying to do some interpretation of the different terms of L or D. So now we'll take an inner product with n hat on both sides. So this becomes lambda dot upon lambda, and then we have an n dot n, and then we have an n hat dotted with an n hat dot, and this is equal to n hat dotted with the vector L times n. Now this is going to be a 1 because small n hat is unit vector, and this quantity here actually is a 0. Let me show you mathematically. So n hat dot n hat is a 1. So this implies if I take a d by dt of both sides, then that's going to be a 0, which basically means that if I take the derivative using chain rule on the left hand side, I get twice n hat dotted with an n hat dot, that's a 0. So that basically means that n hat dotted with an n hat dot is a 0. And this is exactly what I said here, that this quantity is a 0. Another way to understand this is that n hat is some unit vector. By definition, it's a unit vector. Now, when I say n hat dot, that's the change in n hat with time. Now, n hat being a unit vector cannot change in length. The only thing it can do is rotate. Remember the definition of a unit vector? So if it rotates, then we know that for rotation, the change in the vector is always perpendicular to the vector. So what that means is that n hat dot is perpendicular to n hat always. It cannot have any component in n hat direction, otherwise n hat will increase or decrease in size, which is not possible. So if they are perpendicular to each other, then the dot product between them has to be a 0. So what we have is lambda dot upon lambda is equal to n hat dot L dot n hat. And this is something we were looking for. So this quantity lambda dot upon lambda is, it is the rate of stretch per unit stretch, because that's a lambda dot upon lambda, of the element that originated in the n hat direction, because capital lambda dot is defined in an element which was in the capital n hat direction, but now which is in the small n hat direction in the current configuration. So let's write the definition of lambda. So lambda was d small x upon d capital X. So this implies lambda dot is d by dt of this quantity. But remember, d capital X has nothing to do with time. So this becomes d by dt of d small x only and 1 by d capital X, which basically means it's the dot of dx divided by d capital X. I use this bar above to show that it is a dot of the quantity under the bar. So lambda dot upon lambda is going to be d small x dot upon d small x, because d capital X gets cancelled. So this can be interpreted as a rate of change of the size of the element dx, d small x in the current configuration along n hat per unit size of the element. So you see that there's no d capital X anymore. That is what I said, that we start with a discussion with some material coordinates, but we will not have them in the end. So this basically is telling us the rate of change of the length of an element per unit length. Right, so lambda dot upon lambda is Lij Ni Nj, and L can be written as a sum of the rate of deformation tensor, that's a symmetric part, and the vorticity tensor, that is a skew symmetric part, times Ni times Nj. So I open the brackets here. Now this quantity Ni is symmetric, and this quantity here by definition is skew symmetric. And we know that symmetric times skew symmetric is a 0. So this is a 0. So basically our lambda dot upon lambda is n dot d dot n. So this will now help us interpret the different terms. So if I take my n hat, let's say in the e1 hat direction, that is along one of the coordinate directions in the spatial coordinate system. So this means lambda dot upon lambda is simply d11. So I can interpret the diagonal elements of d now, that is the rate of deformation tensor, as the rate of stretching, that is lambda dot per unit stretch divided by lambda, or you can say the rate of extension of the length of the element d small x per unit size of the element. And this is in the coordinate directions in spatial coordinates, because we have an small n dotted with a d dotted with a small n. So all analysis is now happening in the spatial coordinate system, because for fluids the material coordinates do not have much significance. I can also write d small x dot upon d small x is n dot d dot n. So this completes the interpretation of the diagonal terms of the rate of deformation tensor, that is capital D. Now we'll move on to the interpretation of the off diagonal terms of capital D. So let us talk about the off diagonal terms now. So in the current configuration, we take 2 points Q and R this time with the vectors originating from point P as earlier, and we'll call this d small x1 vector and d small x2 vector. So we'll take the dot product of these two vectors. So dx1i times dx2i, and then we'll take a material derivative of this quantity. So this will become dx1 I dot times dx2i plus dx1i times dx2i dot. And this dx1i dot is simply dv1i and so on. And with the definition of the velocity gradient tensor, this becomes vi comma j times dx1j times dx2i plus we have a dx1i, and this dv2i becomes vi comma j times dx2j. Now in these expressions we have a dx1j dx2i, and here we have a dx1i dx2j. So we do some index manipulation. So in the second term, what I do is I swap the indices I and j because they are both repeated. So this becomes dx1j vj comma I dx2i. So now I see that we have a dx1j like here and dx2i like here. So this basically becomes vi comma j plus vj comma I times dx1j dx2i. And this term here is twice of dij, that's the rate of deformation tensor, times dx1j dx2i. And this was the material derivative of the dot product of the two vectors dx1 and dx2. So now what we want to do is we want to link this right hand side which has the d in it now, to the angle theta, which is between these dx1 and dx2. So we basically want to bring in the time rate change of this theta and link this to the rate of deformation tensor somehow. So let's call this 1, and we can also write dx1i times dx2i as their magnitudes, dx1 times dx2 times the cosine of the angle between them. So now if I take a time derivative of both sides, it gives us d by dt of this quantity dx1i dx2i, and on the right hand side we can apply the chain rule. It becomes dx1 dot dx2 cos theta and so on. And then we have a derivative of cos theta, which is minus sine theta times theta dot. So on the right hand side, I'll take dx1 dx2 common, so that gives us dx1 dot upon dx1 times cos theta plus dx2 dot upon dx2 again times cos theta plus, or rather a minus, theta dot times sine theta. So let us call this 2. So we have this equation 2, which has a theta on the right hand side, and we had this equation 1, which had the d on the right hand side. So if we equate the right hand sides for 1 and 2, because the LHS are the same, so this gives us twice dij dxi 1 dxj2. Now remember, d is symmetric, so I written dxj1 and dxi2, but I can swap the indices, it still stays the same because d is symmetric. On the right hand side I have this quantity, and this we'll call b, because this is the equation that will give us an interpretation of the off diagonal terms of d. So in b, if I take 1 equal to 2, that is, I basically say that my vectors dx1 is the same as the vector dx2. Let's call this the vector dx. So that gives me something which we already know. So I'll let you do it, and what you will get is dij ni and j, that is equal to dx dot upon dx. And this is something we already found out earlier. So there's nothing interesting we get from putting 1 equals 2 here. However, if I take my dx1 vector perpendicular to the dx2 vector, then I'll get something interesting. So I'll get twice dij dxi1 times dxj2, and on the right hand side, if you look at expression b, you have a cos theta, and since we have taken the two vectors perpendicular, so cos theta is going to be a 0 and sine theta is going to be a 1. So we have a minus theta dot times dx1 magnitude times dx2 magnitude. So we'll write that theta equals pi by 2. So we can see that we have minus theta dot upon 2, and that is equal to n1 vector dotted with d dotted with the n2 vector. So we just take these on the left hand side, and that gives us the unit vectors n. This quantity here is half of the rate of decrease of the angle theta. And since we have vectors n1 and n2, so that's basically the rate of decrease in the perpendicular vectors n1 and n2. So this is rate of decrease of theta between n1 and n2, which are actually perpendicular. So with this idea, my n1 is e1 and n2 is e2. Then I get minus theta dot 1 2 upon 2, and that is equal to d12. So it's like you had n hats in the coordinate directions like this, which were perpendicular in the current time, and then at a later time you will see that the angle theta that was 90 degrees earlier becomes this angle. So theta dot is the change, which in this case is a negative, but if you take a negative of theta dot, that becomes a positive quantity. So we are measuring the rate of decrease here. You just divide that by 2. It is just like those engineering strains where you divide by a factor of 2. So this minus theta dot 12 by 2 is equal to d12. So the off diagonal terms tell us at what rate are the angles between coordinate directions decreasing. So if the off diagonal term is 0, that means the angle between these two perpendicular elements does not change. Now remember, you're talking about continuous deformation. So that means that under the continuous deformation, the angle stays the same. So the angle between the vectors will not change. And if the off diagonal term d12 was very large, that means the angle is decreasing at a very high rate. So an element like this is becoming something like this. So it seems to be shearing continuously. That is, the angle is continuously decreasing. So I can summarize that the off diagonal terms of D are the rate of shear between the coordinate axes. So this completes the interpretation of the diagonal as well as the off diagonal terms of D. So as a summary, in today's lecture, we introduced the velocity gradient tensor first, and this was followed by an interpretation of the diagonal and the off diagonal terms of D. Of course, we did a lot of analysis on getting the equations which allowed us to do this interpretation. In the next lecture, we will discuss what happens to these quantities D and W under infinitesimal deformations, and we will also interpret the vorticity tensor W. So thank you very much, and I will see you in the next lecture.